The next talk is by Philippe Heim, who will tell us about how to solve infinite state games via acceleration.
So it's pointing up. Yeah, it must not inside, it must hang outside. Yeah, and this one must point up like this, so if you don't mind.
Okay. Does this work? Okay. Yeah, thanks for the introduction. I'm Philippe, and I'm presenting work together with my supervisor, Rayna, and I'm going to tell you how we solve infinite state games with acceleration. And to start, the overall problem that we want to solve is synthesis. So in synthesis, we want to automatically generate some implementation for some system from some specifications such that the system is correct by design. And there are two main directions in synthesis. One is program synthesis. So in program synthesis, what we want to get is some kind of classical program, classical in the way that it gets some inputs and produces some outputs. Yeah, and usually the specification is therefore some relation between the inputs and the outputs, and usually get also you have a grammar that kind of defines what a well-formed program is. And since usually have integers and stuff, right, these kind of programs are usually of infinite state, right? And since they transform inputs to outputs, they kind of represent some kind of data transformation. The other kind of synthesis is finite state reactive synthesis. So there the problem is what you want to get is some kind of finite controller. Think of it as a milli machine, and this finite controller gets some inputs from the environment, produces some outputs, gets some inputs again, and so on, right? It runs over time and gets inputs and produces outputs. And usually because you have this because they run over time, right, you have the specification, some kind of temporal logic. So something like that tells you something over time. And since you have always this interaction between the system and the environment, that the one natural technique that's the main solving technique is via games. So you have a two-player game that's played between the system and the environment. And usually these kind of finite state controllers are used to synthesize, to model some kind of abstract control. Now, if you think about it, usually most realistic systems have actually both, right? You have data transformation and you have some kind of higher control that kind of runs over time. And maybe that's the first thing, that's the problem you want to tackle, and that's also why we want to look at infinite state games, because it kind of combines both aspects. So in the past, the problem has already been studied, and one main method is there a method that are based on abstraction. So the idea is you take the data that you have, you can abstract it to some kind of finite abstraction, and then you reduce this to your finite state method. For example, there are methods to reduce it to kind of finite state games, or to reduce the synthesis problem. If it's formulated and you have a logic that talks about data, you build an abstraction and then you reduce it back to some kind of finite Boolean logic, for example, again, LTL. Another way is to kind of take the classical algorithms, for example, for solving games, and then lift them up such that they can handle the data in a symbolic way, right? So, but both kind of methods are inherently what they kind of do. The main part of the algorithms for this, for example, game solving doesn't differ very much from for the finite state case. And that's why they kind of fail. There's some interesting class of problems with even small examples. I'm going to show you one in a minute where these methods actually fail, right? Okay, so but before I'm going to show you the example, let me introduce you to our formalism. So our formalism, again, that we want to look at now is again a game. It's a two-player game. It's played between an environment and a system. And yeah, so here I have an example. So in this game, right, we have locations, right? And we have variables. There are two kinds of variables. They're input variables. Those are chosen by the environment. And there are these program variables that are part of the state. So they're not directly controlled by the system, but they're kind of part of the state. And then here, for example, then you have guards. So for example, we have this location L0. And then if x is greater than 42 and the input chooses something that's not for I that's not 0, then we go there. And now the system can choose what kind of assignment it chooses, right? The system chooses between the different updates, we call them, right? So in this case, it can either add I to x or subtract I to x, right? And then our specifications are location-based. So this is the thing that the system has to kind of guarantee. For example, you could say something like some locations have to be reached infinitely often. And maybe let's just look at an even simpler version. So this is, again, it's the same game. And we want to answer the question. The specification is that we want to the system has to eventually reach this location G. And now, how would we kind of solve this? So a bit more technical question that we can ask ourselves is, can the system player, can it always force to reach the set of states that looks like that? So that basically means, like in location G, we kind of accept this is like a symbolic representation over these program variables. So this is like the set of states that we want to reach. And the classical technique to actually compute reachability in game solving is the so-called attractor. Right? So the attractor computation, it's a backward computation that kind of tells you in how many steps, right, in like how many steps you can actually reach the target set. So within 0 steps, of course, the target set that we can reach is exactly the set. Now, within one step, the system can actually enforce to reach from L0 if x is smaller or equal to 42. Why? Well, if we are in L0 and x is smaller or equal to 42, then this guard is active, we go there, and then we reach the location G. So within 2 steps, right, the system can reach this target set if x is smaller or equal than 43. Well, why that? Well, if x is smaller or equal than 42, we already know that. If x is equal to 43, and the environment says, okay, it gives us an input that's not 0, let's say 3, right? Then we go here, but then the system can decide whether it adds or subtract I, and for example, if I is greater than 0, so for example 3, the system can choose to subtract I, and then we are again smaller or equal than 42. But now if you continue this argument, you will see, right, so you will get x smaller or equal to 44 and so on. But this computation never terminates. And the reason is that a priori we don't know how many times we have to iterate that. And like the really underlying problem is here that we have to iterate the strategic decisions between this update and this update an unbounded number of times. And this is what the existing approach cannot handle, because they kind of lift the existing game solving techniques. So now to answer the question, actually yes, the system can enforce to reach the set from here everywhere, from every state. And what's kind of the high-level argument here? Well, if x is smaller or equal than 42, and the system can ensure that it can kind of decrement x, like make it smaller, at some point we will reach the case where it's actually smaller or equal than 42, right? And now this is when our acceleration method kicks in. So what we want to now do, right, on a very high level is okay, we know if x is smaller or equal than 42 in L0, we can reach the goal. And if it's not, right, we can go from L0 back to L0, perform some kind of loop, not a real loop, but some iteration, and then in this way kind of decrement. And once we have decremented, right, we know if we can kind of iterately that, at some point we will reach x smaller or equal than 42. So we can also reach from x greater than 42. So maybe let's just formalize our intuition a bit better. So this is kind of this intuitive statement that we have had, and we formalize this in so-called acceleration lemmas. These are basically this triple of first-order logic formulas, and they tell us, okay, if we start from somewhere, so in this conclusion, and we can kind of iterate this decrement, and at some point we will reach this set of states where x is smaller or equal than 42. Or like a more general version, like if you have some sequence of state, right, and you start in this conclusion thing, and you iterate, you can always kind of, from one to the next part, you always do some kind of step, then at some point you will reach into the base. Okay, so now how do we apply this to our attractor computation? So here we had our non-terminating attractor computation, and here I have a schematic version, right? So this is the first set, this is the second set, and so on. Right, and then we have our lemma, and we first check that the system can actually reach the goal from this base thing, like the base, so the base is actually already in the attractor. This is true. And now if we can check that the system, we also check that the system can enforce to kind of decrement x from L0 back to L0, right? And if we know that, because of the property of this of the lemma, right, if the system can always force to do these steps, if we start somewhere from the conclusion, we will end up in the base. And that's why the system can also enforce to reach the goal from in this case from top in L0. And so we can add this top to the attractor in L0, right? So this overall part. And that's why and then we also terminate, because we have reached a fixed point. Okay, so now I claimed that this is actually the case, right? I've explained on a high level why the system can always like kind of decrement, but like how do we check this systematically? So here again we have our game, and the idea is simple. We use a concept we call the so-called loop game. So this is basically the same game, but we kind of split this L0 location into like a source location and kind of a target location. And now we ask, can from L0 can we enforce to reach the step relation in L0 prime, right? So can we actually do a step from there to there, right? Some kind of loop. That's why it's called loop game. And yes, and we can actually check that again with using our attractor computation. And I mean some handling of the fact that okay, this x prime, this x, right? They have to be a bit different because there's no x prime there. And so we know that the system can actually enforce the step relation from L0 back to L0, so we can apply our lemma. Okay. That's how we apply the lemma. Now you can, of course, ask, how do you actually get those? So unfortunately, I don't have the time to explain it. But the idea is basically instead of working with concrete lemmas, we work with some uninterpreted lemmas that are made of uninterpreted functions. And then these kind of uninterpreted functions, we collect constraints over these lemmas. And then we use some kind of grammar and templates to use an SMT solver to actually find like the concrete lemmas or sets of lemmas to kind of instantiate those in our acceleration. And the next question, another thing that I motivated this whole thing with synthesis. So I actually want to get a system that we could run. But now how do we actually extract the systems? And for this, also this is a bit, I don't have time for this, but if you have to do these classical extractor steps, you can actually do a very simple bookkeeping, like of checking what kind of steps you do. And if you have these uninterpreted lemmas, right, that we use here, you have to actually do some kind of function synthesis to actually get the concrete lemmas to apply this. And also this overall lemma, the overall quasi-lemma application, you get some kind of sub-procedures for your acceleration. And also like in game solving, I've shown you reachability, but usually they're more interesting, like specifications for games, like for example Büchi, where we have to visit something infinitely often. And the nice thing is these algorithms for solving those, they kind of use the attractor as a building block. So if we accelerate the attractor, we can also accelerate the overall game solving mechanism. But also we also propose a method how to accelerate this outer fixed point, if you know what that means in these game solving mechanisms. Okay. So we evaluated our approach, and the artifact is available if you want to. We compared it to the different these abstraction-based methods to logic-based ones, and some other game-solving-based one. And also here this constraint solvers that allows us to encode fixed point sets. And we compared on the existing literature benchmarks for these infinite state games as well as new ones where you have to actually do these unbounded iterations of strategies. And here's a subset of our results. So these are these are some old benchmarks, these are some new benchmarks. So this is kind of our tool, right? As you can see, right, our tools can still perform well on the new. So we don't actually lose performance on this literature thing by doing acceleration, because we're always doing this explicit step. But we can solve like these new kind of problems that the existing approaches could not solve. That said, like this constraint solver in some cases actually can really also yield some quite nice results if the problem is fairly small. Okay, so I think that's from my side. So I hope I motivated and I convinced you that this problem of solving infinite state games is actually an interesting one for reactive synthesis. And I've shown you that our acceleration method with which we can accelerate a attractor and therefore like general infinite state game solving. And also we've shown in our revelation that we can actually also in practice extend the scope of problems that we can solve in infinite state games. Okay, thank you. I'm happy to take your questions.
Right, we already have a first question.
Hi, I was wondering, so the theory that you're dealing with so far, just linear arithmetic so far. So there are quite a few tools, like for example, that are more based on, like basically they try to learn the attractors, right? So I know some of them. So how do they compare, like, you know, if you do acceleration versus doing some kind of learning, for example? How do you compare this? I mean, I think I kind of I found several of them. For example, like cosynth from like I think from Andrei Rybelchenko's 2000 something paper. So how does it compare, like this kind of stuff?
So I mean, for the other game solving, I mean, some of these other game solving methods, for example, they're restricted. So we are not only restricted to like integers because we use reals and so on. Like it's kind of independent of the theory. But most of these other approaches, they're either like they're kind of restricted, for example, to safety and so on, or as I said, like sometimes many of these cannot also handle these unbounded iteration things. And yeah, and also approaches that kind of, where you actually have as a user, you have to provide an overall template that kind of specifies.
But your benchmarks are only over integers, right? Or
no, we have also benchmarks over reals.
Okay, maybe reals and integers, so like linear real arithmetic and linear integer arithmetic.
Yes.
Okay, yeah. So those ones are easier to handle.
Any other question?
Thank you. So what kind of problems can you not solve?
Well, like if the acceleration argument gets kind of too complex, right? Our tool at some point it kind of, because also we use an SMT solver at some point, we just run into the limits of the things that we can solve, and also like you have to be able, like if you need an argument that has to kind of fit into kind of that grammar that we kind of provide, that we allow for this kind of template. So. And also you have, since we're using SMT solver, like the arguments have to be in a form that it kind of also can be handled by the SMT solver in a theory form, right? If you start doing stuff, I don't know, with where you would actually need for your ranking argument something where you have like exponential stuff, or you need some very complex like side conditions, right? What has to kind of be invariant under like your loop, right? Then at some point we fail, right? So. Does it answer your question?
I'm not sure. Also, about this step, this is just a technical. Can you go back to that slide where you check? Yes, what does it mean if L0 prime satisfies step this?
This means just that you want to reach that in L0, right? We have this we reach kind of the step relation with respect to, so that means like if actually like there's not the step relation per se, but like you have to start that some initial value that you want to see here has to be smaller than x when you're here, and then you kind of have to compute the attract, and at the end see if the x and the initial value like coincide.
Okay, so the initial value is at L0 and then the last one is at L0 prime, right?
Yeah.
Okay, thank you.
More questions? Okay, maybe one from me. What about parity games or street, Rabin? You handle those?
So I mean, like our benchmarks, we've implemented this thing also for Büchi and Kobuchi. But in principle, you can just, because we accelerate these attractors, you could just implement, I don't know, Selonka's algorithm and then use the accelerated attractor. Right? You could, I mean, there are also cases where we diverge. Maybe this is add where you have to, where this outer fixed points kind of diverges. So like for Büchi, we have some method. We suspect that you can actually extend it to parity also, but we haven't like kind of tried that.
All right. I think it's also worth considering extending this to timed games maybe, which are also often benefit by some sort of acceleration. Any other questions? Okay, then let's thank the speaker again.